Hello and welcome to Electromagnetics 1. Chris Trampel here again. The subject of today's lecture, which is lecture number 4, will be integral vector calculus. Well, as we mentioned before, Maxwell's equations have two basic forms. They have a differential form and an integral form. Certain problems in electromagnetics can be solved in a very elegant way using the integral form of Maxwell's equations. In order to understand these integral forms, we're going to need several foundational theorems, such as the Divergence theorem and Stokes theorem, which are expressed in terms of integrals. In order to quantitatively study these equations, we need to understand vector integral calculus. So let's go ahead and get started here. The first quantity that I want you to consider is called a line integral. If you have a look at the figure in the upper right hand corner of the screen there, we have a vector field that's defined throughout a volume of space. And we also have a contour, capital L there, or a path that's defined somewhere inside the volume. The line integral a dot dl is the integral of the tangential component of the vector field A along the curve L. Well, what does that mean exactly? If you have a look at this expression, you see a number of things. You have the vector, and you have a little differential length. The differential length is depicted here. And this little differential length at every point along this curve is tangential to the curve and has differential length. It's sort of like the dx differential that you see in Calculus 1, only now we've generalized it to 3 dimensions so that it can point in any direction in space. What exactly does the line integral mean? If you look at what's happening, at every point along this line, we're taking a dot product with the vector A, wherever A points, and this little differential length here that points along the line. And all you're doing when you take an integral is you add up all of the components that lie tangential to this path all the way around the path. So if you think of A as a field of force, then the line integral of A dot dl will show you how much force a particle confined to that path will feel, essentially. If A dot dl, if the integral of A dot dl is large, for instance from A to B, then there's going to be a strong force pushing the particle, if you can think of it that way, pushing the particle from A to B. If at every point A is normal to this curve, in other words, if at every point along this line the vector A is at 90 degrees to the line, then the line integral from A to B will be 0. In other words, the field doesn't, in a sense, does not push a particle at all along this line. A particle confined to this line wouldn't move if the line integral is 0, essentially. We have a couple of other definitions here. This is just, as I said, the line integral of A about L. And then if we allow the path to be closed, so for instance we integrate all the way from A all the way around to A, or starting at C all the way around to C in a closed loop, that quantity is called the circulation of A around L. Well, I mentioned before that the gradient is sort of like the 3-dimensional analog to the first derivative with respect to x that you learned about in Calculus 1. And that's really true. In fact, you can actually generalize the fundamental theorem of calculus, this one right here, that you learned in Calculus 1, right? It said that f prime of x dx integrated from a to b is just simply f evaluated at b minus f evaluated at a. Well, a very similar thing happens in 3 dimensions with the gradient operator. If you have a look at this expression, what this is saying here is if you have, let's say you have a scalar field psi that exists everywhere here in this region of space. Again, think of this as a 3-dimensional region now, and we've got some scalar field psi that exists everywhere in this region. Well, if I take the gradient of psi and I integrate it along this path, or in other words, if we take the line integral of the gradient of psi from point 1 to point 2, it is just equal to the field evaluated at point 2 minus the field evaluated at point 1. In exact analogy to the fundamental theorem of calculus for along the real line, essentially, that you learned in Calc 1. Okay, so it's just important, this is just to reinforce a little bit more what exactly the gradient means. In addition to line integrals, we also have surface integrals. Let's start by looking at this diagram here. Again, imagine you have a volume of space, and now floating in this volume of space, instead of just a line, you have a surface. Okay. On the surface, at every point on the surface, we can define a normal vector, a sub n, that is just that. It is at 90 degrees to the surface at that point. And you can define that normal vector everywhere along the surface. And similarly, at that point, you can define, at every point in the surface, you can define a little differential area, okay? A little tiny differential surface area at that point. The flux of A through S, the flux of a vector field A through this surface S, is defined as the integral of A dot n hat, or A dot A sub n, ds. In other words, where before with the line integral we were looking at the portion of the field along a line, here what this is doing is it's taking the component of the field that is at 90 degrees to the surface at that point, and it's adding up all those little contributions all over the surface, and that total, that integral, is the flux psi. Okay. There's some interesting physics that you can understand when you understand flux integrals. For instance, one way I always try to explain this is if you think about water flowing through a pipe, and let's say that you take a cross-section of the pipe, and at every point along the cross-section you can define a velocity for the water. Well, the amount of water that flows through that pipe per unit time is related to the flux of the water through a cross-sectional area. So you'd take think of this A as being now the velocity vector of the water. You take the normal component, the component of that velocity that's at 90 degrees to the surface, and you add it up all across the surface, all across the cross-section of the pipe, and that tells you how much water essentially is flowing through the pipe per unit time. One other quantity that we'll need here are 3-dimensional volume integrals. This is where you're actually integrating a scalar quantity, in this case rho sub v, over a 3-dimensional volume. So we had a line integrals where you're integrating along a 1-dimensional line, surface integrals where you're integrating over a 2-dimensional surface, and also volume integrals where you're integrating a scalar throughout a volume V. Well, in order to use these particular entities, whether it's differential length, differential surface area, or differential volume, we need to think about the particular coordinate system that we've chosen. In this case, this is the Cartesian coordinate system, and this is a coordinate system that you would choose if you were integrating along lines that were parallel, for instance, to the x, y, or z axes, integrating over surfaces, square surfaces or rectangular surfaces that were parallel to one of the coordinate planes, like the zx plane, the xz plane, or the xy plane, for instance, or if you were integrating over rectangular volumes. This is the coordinate system that you would need. And if you'll notice, these little differential displacement vectors, this is the little dl that we saw before, take a different form in each coordinate system. And here, dl just looks like this: dx x hat plus dy y hat plus dz z hat. Okay. Differential surface areas now, if you look at this diagram here, for instance, this dsx is a vector that points along the x direction and has area dy dz. So this first expression corresponds to this little square of differential area. Okay. ds sub y corresponds to this picture, and ds sub z corresponds to this picture. So it's important to understand that differential surface areas are actually have a vector. They're actually vectors. They have a direction associated with them. Okay, and that vector is normal actually to the actual differential surface area. Okay. And then differential volume it has a really simple form in Cartesian coordinates. It's just dx times dy times dz. In cylindrical coordinates, you can see the differential length looks a little bit different. It's d rho rho hat plus rho d phi phi hat plus dz z hat. Okay, so you can imagine, again, you'd use this form if you needed to integrate over lines coming from the origin radially out that over the rho direction, over the phi direction, or over the z direction. That's if you have cylindrical objects, essentially. This is the coordinate system that you will need. And dittos here, just like we have a little different form for dl, we also have a different form for the surface area vector ds. This picture here corresponds to ds rho. You can see that it's pointing along the rho direction. This little slice here points along the phi direction, and this little slice here points along this vector points along the z direction. You would use this particular differential surface vector if you were integrating over a surface of constant rho, right? Like integrating along the outside of a pop can kind of a thing. You'd use this one if you were integrating along over a surface of constant phi, which is a plane basically that intersects with the z-axis, this sort of, like a wedge kind of a thing. And then right here, you'd use this ds sub z if you're integrating over any plane parallel to the x, y plane, essentially. And the differential volume here also, have a look at this, a little bit different than Cartesian coordinates. It's rho d phi dz. Okay, spherical coordinates, same deal. The differential displacement or differential length vector takes this form. Okay, again, you're going to use this if you are integrating over you can think of it as lines of longitude or lines of latitude across a sphere, or lines that come radially out and pass through the origin at some angle, right? And you've got, again, three different surface area, little differential surface area vectors here. This one, ds sub r, corresponds to a surface of constant radius, r, and points in the r direction. This one, ds sub phi, corresponds to a surface of constant phi, okay, which is sort of like the outside of a cone. All right, you'd use this one if you needed to integrate over the surface of a cone, and it points in the phi direction. And then here you have this one here. This one would be associated with a surface of constant phi. Okay, so a plane slicing through at a particular angle with respect to a particular angle relative to the x-axis. You'd use this little differential surface area. And here's the expression for dv in spherical coordinates. Okay, you really have to keep track of the coordinate system and be very careful when you're setting these integrals up. Well, one of the most fundamental theorems and one of the most important theorems in electromagnetic theory is certainly the divergence theorem. And the divergence theorem states that the total outward flux, that's this term here, the total outward flux of a vector field A through any closed surface S is the same as the integral of the divergence, this term here, of A throughout the volume bounded by S. Okay, so here's a picture. You've got some closed surface and you have a volume, and this says for any vector field A, you pick it, any vector field A, if you integrate the divergence of A throughout the volume, you will get the flux of A through the surface bounding that volume. Why is this of importance? Well, it's importance for it's an important theorem that we use to manipulate equations, but it also says something very important about what the divergence of a vector is. Remember, I talked about in the previous lecture that when I introduced the definition of the divergence, that it has an important physical meaning, and we're going to see what that is right now. Okay, let's start with let's choose as our surface the surface area of a cube of sides dx, dy, and dz. Okay, it's called an infinitesimal cube, so an extremely small little cube. And we're going to say, okay, our surface S is going to be the 6 sides of this cube, essentially, centered on this point P. So the flux of A through this surface S has 6 different terms. It's the flux through the front side of the cube, the back side of the cube, the left side of the cube, the right side of the cube, the top of the cube, and the bottom of the cube. That's, if you add those 3 fluxes up, you get the total flux through the surface. Okay. Well, we're going to need something called a Taylor series here for this proof. And a Taylor series basically says that in the vicinity of some point, let's call it x naught, y naught, or z naught, or p. We'll just say p is equal to x naught, or x naught, y naught, z naught. Then we can approximate a function a, in this case the x component of a, as the function at that point p plus x minus x naught times the partial derivative of a sub x with respect to x evaluated at x naught, y naught, z naught, plus y minus y naught times the partial of a sub x with respect to y evaluated at x naught, y naught, z naught, and plus z minus z naught partial of a sub x with respect to z evaluated at the point P. Okay, this is an approximation that is exact as you take the limit x tends toward to x naught. So it's a good approximation so long as you're close to the point P. Okay. Well, using this Taylor series, what we can do is we can say, okay, the flux through the front side right here, if you'll notice, the only component that's going to survive this dot product a dot ds is just going to be the x component of a, all right, through that surface. That's the only component that is along the x direction. The y and the z, of course, dot to 0 there along that surface. And so what we can do is we can say, okay, the x component of a along this front surface right here, using the Taylor series, can be written in this way. Okay, a sub x evaluated at point P plus dx over 2 times the partial derivative of a sub x with respect to x. Okay, times the area here of the front side, which is dy dx. We can do the exact same thing, you know, same song, next verse for the back side. It's the expression for the flux through the back side of the cube. The front, through the back side. And then what we do is we can say, okay, the sum then of the flux through the back and the flux through the front is simply the sum of this term plus this term right here, which when you add these two together, you can convince yourself this is what comes out. dx, dy, dz, a little differential volume, which is interesting, times this partial derivative of x, of the x component of a with respect to x evaluated at p. Okay. The exact same development for the left and the right side, and the top and the bottom give you these expressions. You add a dot dx from the left and the right, you get this piece. It's identical to this, except now you have a derivative of the y component with respect to y. And dittos from the top and the bottom pieces, you have this dv times the partial of the z component with respect to z. Okay, so now we need to add that plus that plus that to get the total flux through the cube. And so interestingly, the flux through the surface of an infinitesimal cube is equal to this expression times dv. And if you look carefully in Cartesian coordinates, in fact, this expression is just equal to the divergence of A. So this is kind of the punchline here. The important thing is that the divergence of A literally means, basically, if you pick a point and you calculate the divergence at that point, what that is telling you is how much, basically, if you put a surface around that point A, how much flux passes through this, how much flux due to the vector field A passes through that surface. That's what this is literally saying right here. So the divergence is literally telling you how much flux passes through a tiny surface that surrounds a particular point. All right, that's what divergence means. If the fields are radiating outwards from the point, you're going to get some divergence. If they don't, then the divergence will be 0. Okay. And then to complete the proof, you just say any volume can be written as a sum of infinitesimal cubes, and so this becomes a surface integral here, and this becomes a volume integral on the right-hand side, and this is in fact the divergence theorem. But just keep that in mind. The divergence is telling you how much essentially how much flux passes through a little tiny surface area surrounding a particular point. That's what divergence is telling you. Well, there's another foundational, extremely important theorem that we're going to need, which is called Stokes Theorem. And Stokes Theorem states that the circulation of a vector field A around a closed path L, that's this term, is equal to the surface integral of the curl of A over the open surface bounded by L. That's this term here. Okay. Well, remember, we talked quite a bit about line integrals like this. This, I think, is pretty clearly just simply the line integral of A around a closed path, right? The circulation of A. Okay, so we have some idea what that is. It's just the dot product of A with a little differential length dl at every single point and added up all the way around. Okay, and what the Stokes theorem is saying is that, remarkably enough, whatever the integral of A dot dl is all the way around this path is somehow related to the curl of the vector integrated over the surface bounded by that path. Let's see how that works. Let's see how that might work. We're going to play a very similar game to the one we played for proving the divergence theorem, except now we're going to take, instead of a differential cube, we're just going to take, or an infinitesimal cube, we're going to have an infinitesimal square. And the infinitesimal square has sides dx and dy. That's it. Okay, it has 4 sides, 1, 2, 3, 4, 2 of length dx and 2 of length dy. And we're going to say this is the point right here, x0, y0. All right, and this is the point xy. Okay. Well, now instead of worrying about the flux, now we're interested in the circulation, right? And so the circulation is just A dot dl, and in this case it can be broken up into an integral over each of these 4 paths, 1, 2, 3, 4, just like this. Okay. Again, using well, just using the definition here, we can say that in an approximate sense, if we say that this distance is small enough, then we can say that the vector is constant along this distance. So we can say that the circulation is approximately along here. You're going to get the x component of a, all right, times dx. Along here, you're going to get the y component of a, dy. Again, the x component up here, and here the y component. That's what each of these pieces are. And the sign differences here just simply have to do with the fact that here along this integration you're going from here to here, and then you're going in the opposite direction from here to here, so you get a minus sign. That's where those signs come from. Okay. And you'll notice you are evaluating the fields at slightly different points, but at least along this direction here, you'll notice we're allowing we're just saying the field is basically the same as it is in the middle of the line segment and so forth. Okay. Anyway, important thing is this is an approximation to the circulation of A around this little infinitesimal square. All right. Again, we're going to use our Taylor series approximation right here in this form in the x direction, and in this form in the y direction. All right, so just keep those Taylor series approximations in mind. Okay, when you substitute in for these expressions using the Taylor series and add them up, you get the following right here. Partial of x with respect to y times this little differential area now, interesting, this is just the area of the cube, and plus this partial of the y component of a with respect to x times again this little area, which is just simply the area of the square. And in fact, if you look at the definition of the curl, you'll find out that this expression is this piece right here is just simply the z component, the component of the curl directed normal to the surface of this square, times the area of the square right here, times ds. So this is saying something extremely powerful about what the curl means. Okay, what the curl means. What the curl of a vector at a particular point is telling you is how much is the circulation of that vector field around that point for a very small contour around the point, basically. How much does the vector circulate around that point is how you're thinking about it. So the curl literally is a measure of how much the vector circulates around a particular point. That's what the curl is telling you. As we will see in the electrostatics and the magnetostatics lectures, the curl, the circulation of this vector, if you want to think about it, the curl and the circulation are sort of equivalent. The circulation of the vector about a point is what creates propagation. It's what allows information to move from point to point. And we'll see how that works once we get to electrostatics and magnetostatics. Okay. Again, just to finish the proof here, any surface area can be written as a sum of particular surface area of infinitesimal sized surface areas, and so therefore we get the final form of Stokes theorem, which is circulation of A around any closed path is equal to the curl of A integrated along the surface bounded by that path.